Hello everyone, my name is Francis Tiong and I'm hosting for today's Bish Bash. What is Bish Bash? Bish Bash is an informal networking meetup hosted by technology companies for people working mostly in audio. And Bish Bash has been around for a long time. I see that there is that company audience here, and there was a long time ago. The audience is no longer there. It's been bought by Nose, and must have been like 14 years ago. I know that because I was in audience and I was in Bish Bash back then. And what is the point? The point is that we can learn about the latest advances in audio and related fields. We can share our knowledge. We can meet some people, have some food, just have fun. So this is a really exciting event for me. My name is Francis Tiong. I'm with MathWorks, and here are the other organizers. There is Oreo, Kamal, Safar, Frederick, Karim, and they've been around much longer than me. I mean, as an organizer. Okay, so we have a Meetup channel. We have a YouTube channel. In the YouTube, you can find the other meetups recorded as also. And so let's help spread the word. Now, this is an event that I've been asked to promote.
Hey, good to see you. Oh, you want to talk?
Sorry, I'm late. It was incredible. Okay. I just wanted to say, well, thanks for coming, everyone. We're excited to have an event for organizing this year. MathWorks. And just briefly to say that we are organizing this year the International Society for Music Information Retrieval Conference in San Francisco. It's going to be in November. If you have submitted your papers, wish you best of luck with the review process. And yeah, I hope to see you in San Francisco in November. We're really excited to have this conference this year for the first time in the West Coast. So yeah, see you there. All right, thanks for coming. Thanks for organizing.
Okay, so this is the agenda for today. I will be talking about spatial audio modeling first. This is regarding simulating the acoustics in a room. So first you can scan a room and then you can simulate where are the sound sources and where you want to pick up the sound. And from there you can try to find out the transfer function of the room, and then the room acoustics can then be rendering out after that. So after my talk, then Dr. Stephen Thompson from Penn State University, he will be talking about simulating a clarinet model. So actually simulating the sound that will be coming out from this musical instrument. So that is very interesting. And next, Brenda, she will be showing us how to do compression, for example, changing from floating point to fixed point and compressing your network, and how to tune the performance for the neural network before the deployment. And after Brenda, Matt Daly will be on, and he has a paper that won the IEEE challenge, and he's going to tell us more about that. And last but not least, Eo Emir from Modolix, he will be talking about reactive sampling and beat pizza slicing. And I can't wait to see that. I would like to introduce myself first. My name is Francis Tiong. I'm with MathWorks. and I've been working with MathWorks for 5 years. Before MathWorks, I was a consultant, and I like to use this slide here previously shown. Yeah, this one, it has a few of my old companies here. So before I was a consultant, I worked for Knowles, Knowles, in the middle top. So I was implementing speech recognition, noise suppression, echo cancellation, that kind of systems. And Knowles, I was in there for 5 years. And before Knowles, I was in audience, and Knowles bought audience. And I was in audience for about 4 years. And audience was making pretty much the same thing. They have this sound processor that ends up being used by iPhone 4. And before audience, I had my own company making MP3 systems, MP3 players. Specifically, those are boom boxes that I was making. And I had my own company for 8 years. So that's a brief history. Let's get on with the topic of today. Okay, this is today's topic, spatial audio modeling in MATLAB. And if you would like to get a copy of today's slides and example code, please send me an email. I will also try to put up a link on the HRTF site so they can download. If you're in the room today, here is the Wi-Fi password that you can use. Please shoot me an email. Okay, I'm going to show you an example first. In iPhone 12 and up, there is a LiDAR, and you can use this LiDAR to scan this room that you're in and obtain a physical model. This model can then be converted into an STL file, and the file can be loaded onto MATLAB. You can then simulate microphones and loudspeakers placement anywhere in the room. The goal here is to simulate the sound received by the microphones. In MATLAB, I can run a ray tracing algorithm and find out the transfer function between a microphone and a loudspeaker. With the transfer function, I can then render the sound received, which includes the room acoustics. Now you can get this code or this example that I'm showing you with this LiveScript file through this link here showing it has been posted up in MATLAB Central, and it's really documenting what I'm about to show you. Okay, so this is what it looks like when you loaded the file in. But before that, I want to show you that room. Yeah, so this is an example what it looks like after you have scanned using your iPhone. It's quite a lot of details, ceiling, floor, all the details included. Now I have another example here that it looks like a DJ playing music in a garage. There you go. And in front of him, there are these two loudspeakers. That's where I want to simulate the sound coming out from those loudspeakers. And the audience right in front of him, this guy here, I'm going to simulate just like what is the sound arriving to right in front of him. Now, after you converted that file into STL and loaded into MATLAB, this is what it looks like. The first thing you noticed is that the orientation might be off. I don't want the Z-axis to go straight up. So what I'll do is, so after you loaded this file in, there's supposed to be a triangulation object or a matrix that's created. So what I do is I create a new triangulation object and copy the array from the from the original one, loaded one, to the new one, but with the dimensions flipped. You can see that here the second dimension becomes the third dimension becomes the second. So essentially, the axis would have been flipped. And with this new triangulation object, now I can save it into a new file, STL file, and use it. And you can pretty much do the same trick if you want to scale the whole room also. Now with this new object loaded, next thing is I want to place the speaker and microphone locations. Right now I'm only showing placement of one loudspeaker and one microphone, but actually you can put more than that. These coordinates is pretty much the XYZ dimension. You can see that the loudspeaker after placement there's a red dot and the listener has a blue dot in front. So that is the transmitter and the receiver. Now I can proceed to run the ray tracing function. You can see that I set the model and then just run the ray tracing. The result will show a lot of rays bouncing off. And let's look at the last ray that's arriving to the receiver. And because usually that's the one that you have the most, I would say, information or interaction with the room. So look at the last ray. You notice that the structure also showing the original transmitter location, receiving location, the angle of departure, angle of arrival, and in the end you see there's a number of interactions, 10. That is to say how many reflections or how many interactions there was. And for each of the interaction, you can see that here, this array here, interactions, I can trace back and find out what are the points or locations that it was bouncing off from. And from there, I can deduct the materials or how it's supposed to be attenuated and all that. We can get back to it later. So the number of interaction was 10. That's because earlier here, when I do the propagation model, I specify the maximum number of reflection is 10. Actually, a lot more parameters that I could have programmed in. For example, there is the resolution of the angle I can put in, like what is the smallest angle that I want to include as in a simulation for each of these rays. And so after getting the rays, the next thing is I want to put in the reflection, the absorptions. Basically, I want to find out the path loss. And the path loss is based on each of the rays' propagation distance. Now, this part of the function that I'm showing you, calculating the path loss and all that, it will be absorbed in later versions in MATLAB. But currently, right now, we have to recalculate it because the default values inside this ray structure, it's based on RF calculation. It's not acoustics. So for each of these distance, I have to attenuate it based on this simple acoustic, like 6 dB every doubling of the system, doubling of the distance. That is the path loss. And you can see this line here at the end, I have 0.05. That is the absorption material, the default one that I want to use for this object. And to be specific, let's say if I want to say the sidewalls having a different reflections absorption, then I would do it like this. I would write a loop and then detect the locations where the walls occurred, where the interaction of the wall occurred, and then from there I can add in the additional absorption. Now, if you look around the internet, you'll find these documents, these data that shows the acoustic absorption coefficients. There you go. And this is brickworks. There are like plaster walls, glass windows, wood, stage floor, carpet. So there are a lot of data that's available. And you can see that the values I've used is basically from these tables. These are absorption materials. And you also notice that it's actually frequency dependent. Like for different frequencies, the absorption is a little bit different. And so ideally, I need to make that a multi-dimensional simulation, but for now, I'm using just one default frequency. So actually, so that's how I put that in. So for the walls, I have that much additional absorption. That 0.02 is the additional absorption based on the material table. And from there, I loop through it. I can find out the ray path loss for each of the rays. Now, after getting path loss, I want to get the delay profile. And the delay profile can simply be the propagation distance divided by the speed of sound. And that's how I calculate, that's how I got the delay. So moving on. So this is the path loss that I've got after the simulation. And ultimately, I would like to simulate render the sound back out. And I would need to simulate that in two parts. So the first part would be, well, including these early reflections. And you can see that these ones here in the front is probably the direct path receiving it. And then after these, there will be these early reflections that's coming in. And after the early reflections, there will be these long delays or reverberating tail that's reflecting from more delayed reflections coming back. And so with that part, I would need to do it using this reverberator. But this is a good picture of it. You see that the early reflections and the mid reflections, and then after that following by a long tail. And this is this long tail that I need to simulate using this reverberator. And these early reflections and the mid reflections, those I will be implementing it through an FIR filter. And the tail is using the reverberator. So let's get back to the code. And after the reflection is done, the simulation is done, right? I need to say chop it off to say at which point I'm using FIR and which point using the reverberator. And so pretty much all the ones that's lower than 30 dB, I'm saying that it's from the FIR. So the early reflections we have to deal with after quantizing it, you'll see that there will be multiple angles arriving at the same time. And these I want to project the ones from different angles back onto the look direction. So simulating that the look direction here is the main path that we're focusing in. And after doing that, then I would have gotten an FIR filter tabs, and these are the ones. And after the delay path is done, now I have to find out the reverberation. The reverberator tail that I've mentioned earlier over here, it has this long tail. I have to find out the slope of it. Now that can be done using this Sabine's formula, where it's estimating the RT60 value. RT60 is the time that it takes for the signal to die off 60 dB. So using this equation, after I put in the dimension of the room, I find that it is about 1.2 seconds. And with that, I can calibrate the parameters needed for the reverberator. And that turns out to be the decay factor is 0.95 and the wet-dry mix is 1. And with that, now I have all the components that I need. I can read in the wave file and do the first part, filtering, using the delay profile, and the second part using the reverberator, adding them both together and achieving the final rendering sound. Now, after getting the sound, I guess I can play it out. We have this audio viewer object that you can just view the picture, view the wavefile, and also play the sound as well. So let me see if I can play it now, and you can listen to the sound. Let's see here.
Testing is the process of trying to break the code. Testing leads to failure, and failure leads to understanding. If debugging is the process of removing software bugs, then programming must be the process of putting them in.
So that was before processing. Now this is after.
Testing is the process of trying to break the code. Testing leads to failure, and failure leads to understanding. If debugging is the process of removing software bugs, then programming must be the process of putting them in.
So that was the audio file. Actually, I'm not sure if you can hear it well because there's only a little bit of echo created, and when I play it out in this room here, there's probably more effect from this room than the other one that's going to affect it. All right, so let's say after I have sound recorded at this one spot, now there are two scenarios that can arise. Number one is, what if it's not a recording device? What if it is an internet gadget like those, let's say Alexa, for example, devices that is actually using a microphone array to capture like the speech command? The second question is, what if it's actual person perceiving the sound? What are those two scenarios going to look like? Well, in the first case, where the wavefronts from different angles are arriving at this microphone array, what we can do is, I have an example here that's actually in Simulink, that I can simulate different wavefronts. Let's say there are 20 wavefronts arriving at all these different angles. What I can do is put in this example, this file here, arranging to have all 20 wave files on the left here, and all these 20 wave files going into the microphone array block. And with this input, I will also have to specify all 20 angles for each of these files that's specified in this pink box here. So I have 20 wave files and all their respecting angles of arrival going into this microphone array block. And this microphone array is like wideband RX array. I click in here, and you can see that you can specify the directivity of each microphone, whether it's omnidirectional or not. You have to specify the geometry, like whether it is uniformly linear array, whether it's uniform circular array, or it's custom size. And you can also put in the spacing between microphones, and also not to mention the number of elements. So let's say if I have a 10 microphone arrays, then at the output of this block, it'll be a 10 channel feeding into the next block. So with that scenario, now you can simulate it, and you can now continue to simulate the case where you have a beamformer, for example. And that is a simple example, and this example is also available on our website. You can check it out. Now, the second scenario would be, what if now I have the sound arriving to a person, and what would that person hear? Now, that obviously depends on the physical size of the person. For example, what's the size of his head, what size of his ear, all that come into play. And all that comes together will form we call it head-related transfer function, HRTF. So each person will have one set of HRTF, but MATLAB here, we have generic data that can just let you simulate HRTF as a standard person, but you can put in your own different size of different person as well. And not only that, MATLAB also do the interpolation for different angle of arrival. Let's say you have recorded at like a set of arrival, and then we can simulate what's between these measured sets and interpolate the results for you. So that comes into that leads into our topic of SOFA files. SOFA files are spatially oriented format for acoustics. These files holds the HRTF impulse responses, and we have a way to display all these points and different visualization tool that's all available. And I have actually a live script file that I will show you later on. But let me explain this first. This is the latest one from released in 24A. Each year, MATLAB has 2 releases. There's the 24A and there's the 24B. The A version usually released in April, and then the B is around like October. So in the latest one, we have added a lot of visualization tools for displaying all these SOFA files and the responses that you have recorded. So let's go take a look at it. And I apologize, there's some message that's been sent to me, but I will not be able to respond at this time. All right, so the SOFA files are like a very popular format for holding these transfer functions. So once you have loaded them into MATLAB, and you can then visualize them, and basically they are just basic impulse responses like this one here. But per angle, per person, there'll be like a one set of impulses. So if I look at the spots that's covered for all the angles covered in this particular SOFA files, you can see that there's like a lot of them. And from there, you can look at the impulse response from different angles, the frequency response from different angles, and this is like the angle versus frequency, and it's just like a nice display of it. And you can also look at the energy time curve and the response, and also this is a different angle of arrival plot. And so just please check it out. We have a lot of visualization tools for that. Now, this is the end. Like people would ask me, obviously, after I have simulated the sound, like I have did in this 3D room, how do I verify that it's really what it should sound like? Well, we have examples posted on our website that you can check it out. One of them is 3D sound event localization and detection. This one, what it does is that you can use 2 ambisonic mics, and you can go to a real room, you record the sound there, some sound event happening there, you recorded it, and using those data to train a neural network. And that neural network can then tells you what is the source of the sound, what is the direction of arrival, all that. So using the real data, you created this network, and then you can swap in the synthetic ones, the simulated ones like we have done earlier, and then to see if indeed it gives you an accurate angle of arrival and resolution using this neural network as an example. The other example I have, 3D speech enhancement, that's simply saying if I record it using a sound using ambisonic mic, and I can use this simple neural network to enhance and bounce the output back to maybe a stereo sound, and it actually enhance the speech quality. So that was for the second example here. So this is pretty much what I have to say, and there are a lot more examples you can find. I want to add that I've talked about ambisonic, so we do have more ambisonic encoder decoder examples available on our website. Please check it out. And this is all I have to say. And I want to add that we are hiring. So if you can scan this QR code, you can see if that's interested of you, or you can just send me an email if you're having trouble connecting to the proper hiring manager. So that's all I have. Thank you very much, and thanks.
So let's see. Thank you. So let's see. The next one is, sorry?
Please not coming over. Can you check before the next presenter?
Sound. Oh, I mean, when I play the sound, it's not coming in?
No, when you're talking.
But in house, it's not coming in.
Thank you
Yeah.
much.
Oh, really?
Yeah.
Okay.
Can you just do a quick test with the audience on the phone? You just ask them if they can hear you from here.
Can you hear me? Can you hear me, Dr. Thompson? Oh.
I can hear you, but it's coming through fairly reverberant.
Oh, I see.
I could not hear when the when you were trying to play sound from MATLAB. I did not hear that.
Oh, okay. I see. Yeah, when I shared just now, I have to click. I have to click enable sound. Okay, so now it's. Sorry.
Go ahead.
Okay, Dr. Thompson, you ready?
Yes, let me share. And I need to include sound. And I'm going to share this. Okay, do you see my screen? Hello, I'm not hearing anything from your end.
Yeah, I muted myself.
Okay.
Yeah,
Okay, good.
I see you fine.
Yeah,
Very
and I
good.
can hear you're fine.
Very
Great.
good. Okay. I'm going to talk about a time domain model of a clarinet-like system using Simscape. Simscape is the physical systems modeling part of the MathWorks product line. It rides on top of Simulink. Simulink is a signals-based computation. The Simscape is a physical signals based, much like an electric circuit simulator would be, where if a connection carries both voltage and current. In Simscape connections, in the electrical domain, it's voltage and current. In the mechanical domain, it'll be force and velocity. I'm going to talk about an acoustical domain, which is not part of the standard product line, but it's a package that I've written and is available on the file exchange. But to think about the physical system that we're modeling, a clarinet, let me get this set up right. Okay, so clarinet is a mouthpiece and an air column. The air column may have tone holes in it for changing the effective length of the tube. And a player will put their mouth over the end of the tube. They do a lot of crafty things with their embouchure, with their lip pressure against the reed, but basically this leaves a small open slot for air to pass in here, and they put air pressure from their lungs into the mouth, which sends air down into the system, and that alone is enough to start the reed vibrating and creating the dynamic signal that becomes the music that comes out of the air column. That happens because of a kind of an unusual thing that happens up here with the reed, and that is that as the player blows harder, increases the pressure in the mouth here, they'll start to push the reed shut a little bit, so that initially when they put air pressure, there will be a certain amount of flow. When they blow harder, there will be a little more flow, and that is a lossy kind of a mechanism. On the other hand, as they blow harder and harder, the reed starts to go shut, so that the curve of pressure difference between the pressure in the player's mouth and the pressure in the mouthpiece, in the static case, is if you just increase the pressure in the mouth to increase this pressure difference, the flow through the reed starts to increase, but as the reed goes close more and more, it will come up here to a peak and eventually will start to go on back down. In this region, this is a positive resistive impedance between the pressure and the flow. But over here, you have a negative impedance, and that negative impedance is what allows the thing to self-oscillate. The player needs to get the blowing pressure up across this peak, but once it starts on down here, there is a negative impedance in the system that allows it to begin to oscillate, and that's basically the way the system works. The model that I'm talking about is that kind of a clarinet, and let me come over here. If this is a clarinet with the mouthpiece at this end. There's a region of closed tube with no holes in it, and then here you start to have tone holes that allow the player to open or close those holes to change the effective length of the tube. The way that's modeled down here, this is that length of closed tube with the mouthpieces over here. We'll talk about that in a minute. We have the closed tube coming down to the first open tone hole. This is an acoustic transmission line, a part that is written in the acoustics library that I mentioned I have written and put out on MATLAB, the file exchange. So this is that closed transmission line coming to the first tone hole, another segment of length going down the tube to the next tone hole, tube, tone hole, going all the way down. This piece on the end is a radiation impedance that gets the correct pressure and flow coming out of the open tone hole. In a different model than the one I've shown here, it's possible to open and close these tone holes so that the model can also change the effective length of the tube. This particular model is set to only play one note down essentially with all of the holes open. So that's the way this works, and these things also come off and allow you to read off the value of the far field pressure that would be radiated from that tone hole. The effect of the tone hole lattice here, this row of fairly regularly spaced holes, the effect of that is to take what would have been an essentially infinite series of resonances at the frequencies that are ratioed 1, 3, 5, 7, 9, and all odd harmonics, which is what you would get with simply a tube that was cut off here and didn't have the tone holes. The effect of the tone holes is to create a cutoff frequency. So in this case, for the B-flat clarinet, at about 1500 hertz, all of those higher level resonances are made to go away. This is basically it's a low pass filter that allows these resonances to stay and these ones go away. That actually makes the instrument much easier to use, to design and to work with. So for most of the notes on the clarinet, there will be 2 or 3 relevant impedance peaks that the tone is based on. And when you get the blowing pressure up high enough to overcome let me get back to this curve again. When the pressure gets up to, this point is called threshold blowing pressure. Once you get above that, now this is going to start to oscillate, and it will oscillate at the frequency of the highest peak and begin to oscillate as basically a sine wave, only with that component. But as you increase the velocity, the nonlinearities will generate really all harmonics. The third harmonic will be picked up and aided by this extra peak. So excuse me, this is our model, and the reed and mouthpiece are up here. Let me show you a close-up of that. The reed is simply a single degree of freedom mechanical oscillator. This is a mass spring damper using the standard components in the Simscape library for mechanical components. And the motion of the reed then opens and closes the reed aperture so that the blowing pressure that is put in here will put in a dynamic flow. That flow is calculated down in this box, which is a piece of code that I've had to write also. The equation for the pressure difference is this, with this being the velocity of the reed. The so that the flow goes into the air column, and the pressure in the air column then comes back and exerts a force on the reed that causes the reed to move back and forth. And all of this then starts as a self-oscillation. The blowing pressure that I put in is going to be at about this level. This is about 1,500 or 1,600 Pascal, which is a normal blowing pressure for clarinet playing. But I don't increase it instantaneously. I put in this sort of slow rise. That helps both. It's both more realistic because players can't do an instantaneous rise either, but it also makes the MATLAB solver a lot happier. This kind of program really hates instantaneous changes. So putting this in as a somewhat slow rise, and I'm doing this over a 30 millisecond time period, which is reasonably quick, but not instantaneous for the solver. These are the waveforms that get generated at various places in the clarinet. So this blue here is the blowing pressure that I put in. The red, this is the pressure that builds up in the mouthpiece, and you'll notice that it kind of doesn't get really started until we get to over the threshold blowing pressure. But in this region, it's starting to grow from 0 up to a fairly large value for the pressure in the mouthpiece. That pressure also propagates down the tube and radiates out of the tone holes, that's not shown here, but is a feature of the model. The other thing that's important, the reed position. I mentioned that when the player starts to add the blowing pressure, that pushes the reed shut partly, so that when the pressure reaches maximum, the reed has gone partly shut. Now this is a reed that's open 7 or 8 tenths of a millimeter. So it's only about halfway closed, a little less than halfway closed here. And the pressure in the mouthpiece puts a force on the reed that causes the reed to move back and forth. And this now is the airflow coming in from the player's lungs in through the reed aperture to make this thing play as it begins. What happens then if we go back and think about that curve of pressure difference versus volume flow? Statically, we're following this curve up the value that I showed you before. We get to threshold, and it begins to go down the other side, but now we're in this negative impedance region where it can begin to oscillate. And what happens is that it starts to go up and down. Well, this is a close-up of what it's doing. It's kind of spiraling around there. And eventually, when you get to a very high playing amplitude, again, it started out coming up here. It started to spiral out, and now it's doing some fairly large amplitude vibrations, oscillations that follow a path like this. So, as an example, this is using the version of the model that has the ability to switch the tone holes open and closed. So what I've got here is a tube. Now this is going to play 3 different notes because I can open and close these holes. So here, this again, it starts out at 0. There is a fairly quick rise to a steady state while I'm holding the all of the holes open. I close the first hole. It changes frequencies, and so let me just play it here. Why isn't it going? Because I have the pointer set wrong. Okay. Play that again. So that's actually the waveform recorded in the mouthpiece. It's not the one that is out through the tone holes. It's a little easier to get this one, and it's the one that I had at that time. The radiation from the tone hole would be basically the same, but a little brighter. You get a little more high frequencies radiated from the tone hole, but the basic timbre would be about the same. So it's a model that the first time I actually heard this thing, I was happily surprised, because what you've got here is a model that it's got all this, the acoustical model. It's basically tubes in a piece of wood, the reed, and a DC pressure that causes it to be excited and radiate in this way. So let me go on to the other. Thought that was gonna. Okay, so I can take questions. I will say that this week I'm in Ottawa, Canada, at the meeting of the Acoustical Society of America, jointly with the Acoustical Society of Canada, and at one of the annual meetings up here. I gave a slightly more advanced version of this topic at one of the musical acoustic sessions here yesterday, and it was actually answering one of the research questions about, does this model have enough resolution, enough accuracy to be able to answer some of to at least replicate the kind of behaviors that have been known for this transducer for a long time, for this transducer, the clarinet. One of the things that's important, I mentioned for the clarinet, is that those resonance peaks be very accurately aligned at harmonic. The second resonance be at exactly 3 times the frequency of the first one. If they're off a little bit, the clarinet won't play as well, and at least professional players will hate it. What I was able to show this time is that if you take a tube where the impedance peaks are accurately matched at a 3-to-1 ratio, and compare it to the performance of one where they're off by about 1%. And 1% is a fairly large number in musical terms. That that you have much better playing behavior. That the if in the good one, if you do play a crescendo, it plays nicely on the same frequency. On the bad one, if you play a crescendo, the frequency changes, and there's not much. I mean, the player would have to work hard to keep that from happening. So I would be happy to take questions if anybody wants to take questions, wants to answer questions, or I'll turn the rest of the time back over to the group.
Okay. I'm a bassoonist and also a MATLAB hacker, and I've long had the idea of making a model of the bassoon, and I'm wondering how much difficulty it would be to adapt your model. The difference is the bassoon has a conical bore. It's a very shallow, a very narrow cone that goes all the way from a couple of millimeters up to about 30 millimeters, and that means that it behaves rather differently, and it's also it's open at both. It plays as if it was open at both ends, so you have all the even and odd harmonics.
Yep. The conical instruments, the components that you would use here, these are cylindrical components. Having conical components is included in the library, so modeling the bore is not the problem. The challenge is that the bassoon is also a double reed, and the behavior of the double reed is kind of similar, but not quite the same. And I'm not sure that the pressure versus flow curve that I'm using would be right for the double reed. We'd need to look at that. Now, I say that I say that as if I have a really competent model of the clarinet, and as I said, I'm quite happy with what it's been able to do. But there's a lot of difficulty in getting this thing to be playing more than one or two notes. So I'd be happy to work with you and try to get something that was somewhat reasonable. I think we would be able to find data for what the open and closing curve of the flow curve of the bassoon of a double reed would be. So I think I'm going to give you a kind of a weak answer that says you could probably do it, but that's without having any experience in having done it.
Well, there are some papers on the reed. Most people think that the reed fully closes during a significant part of the cycle, but that's a more complicated question. But I'll send you an email and we'll see what we can.
Okay. As the clarinet reed also slams shut when you get above about mezzo forte. I've not shown that here, but there is, let me go back to the laser pointer again. There is an additional component that can be put here that they call a mechanical hard stop that will allow for the mechanical motion to come over, get to a totally closed position and stop, and then wait for the pressure in the bore to become big enough to push it open again. As I said, the clarinet above mezzo forte plays that way. I have done a little bit of playing to see that I can make the hard stop work correctly. It slows the model down quite a bit. That getting around those sharp corners is not easy. And it's already not a very quick model. I didn't tell you that it probably takes, I can't remember for sure whether this was a 12-hour or a 48-hour calculation to get it done, to get the 2 or 3 seconds of
Not exactly a real
time domain done. But I'm happy that it sounds pretty good.
It does sound like a clarinet. Have you tried compiling the code? Because MATLAB can probably compile it.
I have not tried to compile it. The last time I thought about that was several years ago when I believe the compiler didn't handle all of Simscape code. I believe it does handle all of their Simscape code now. I have not asked whether it would handle mine.
Yeah, we have discussed this before, and to use the compiler, it's best that you do it in discrete time. And in this case, you want it to be variable time, so it makes it a bit harder. But we are looking into this.
Yeah, I'd be interested in kind of corresponding with you two on that.
That'll be great.
Yeah.
Yes.
Sorry, there's another question, or yes?
Okay.
You're gonna get picked up by the microphone back here.
Can you hear?
What's up?
Yes, I can hear you fine.
Okay, so apologies for not having time to review literature, but given the long history of physical modeling instruments, I'm assuming that people have tried to do this before. So what's the new angle in the model here?
There's been a lot of work done, but most of the people who are doing this are trying to do it in ways that allow for really quick responses. They're linearizing things. They're using linear systems analysis, and they're kind of faking the fact that the model really, if you're going to do the linearization things that they're doing, the model really needs to be time invariant, and it's not time invariant if you're actually going to do anything to change the open and closed tone holes. So there are things that have been done. This model, I mean, I think this model will have the ability to, because it's more intuitive the way it's put together. I think it'll have more of an ability for people who are not modeling experts to be able to get in and work with it and make it do things. But it's
Yes, I think I can also add to it. Like, first of all, Simulink is a analog simulator. It does not discretize anything. And second of all, it's a multi-physics, multi-domain simulation, meaning you can simulate like mechanical systems together with gas domain, mixed domain. You can simulate everything together at once. So this gives you some advantage. Like, you can model something that's in a more straightforward way, and yet you preserve the precision. So
yeah, and if the literature you're talking about, there's a group in France that writes all of their own code. It's all, as far as I can tell, it's all custom code, not really very commonly shared. And they are able to do a lot of what this does. But again, I think that this is a much easier to approach without having to write all of your own custom solvers and everything.
okay, sorry, we're running low on time. Can I talk to you after that? There's one more question. I can address that later.
Okay.
Okay. So Brenda, are you ready?
Yes. Are you able to hear me fine?
Yes, I can hear you fine.
Okay. So, and I will also share my screen.
General.
Yeah. Are you able to see my screen as well?
Yes, yes, you can see.
Okay. Well, I could let Professor goes on for another 5 minutes. That's fine. It was I was learning a lot along the way as well, so I don't mind. Okay, so I am Brenda. As you probably can tell, it's dark outside, so I am working in the development domain at MathWorks, and based out of our headquarter Natick site in Massachusetts, so East Coast. I am not a acoustic expert, and most of my actually work experience comes with embedded software, really developing, and software engineer actually working in developing features in MATLAB and Simulink. So that's why when Francis mentioned to me that there is an interesting kind of forum like this, and he asked me if I have any interesting topics I would like to share. I was like, okay, speech, can I do my, command recognition spiel? And he said, no, that group, that is too kindergarten for the group. So I instead wanted to share a little bit of some of the interesting project that's more based on just simple digital signal processing rather than very specific. So for acoustic, hopefully, the topic is still relevant for this group. Another angle that I would like to share in today's chat is about how do we really take an algorithm design sometimes in these days are described with neural networks and being able to really look into how to get it ready for deployment. So I have a catchy term to call it nest to bytes. But for today's conversation, actually, I would not show C code or anything like that for that purpose. Okay, so what is that example I would like to talk to today? I kind of want to go back to, I squinted really hard to notice that there's also, women engineers in today's meeting. I know there are a few math workers of them as well. So this may not be a foreign story for you. But I wanted to anyway, if you have, if there are mothers in this audience, or if you forget to tell your mom that Happy Mother's Day, you can still do it. So I kind of wanted to take you back to quite a few years back. When I was expecting my first kid, one thing I do is, of course, like any good, academia, we wanted to read the books. And this has happened to be a book probably being more than 50 years now. And like the title says, it tells you a comprehensive month-to-month formatting to explain what to expect. That's all good. I read every chapter, I dog ears all the content that are very important to me. But there's also things that when I actually go to visit my doctors, I realize that there are also things that are not written in that book. And sometimes those are pretty surprising. Again, I couldn't quite see the audience very well, but I don't know if all of you have actually seen one of this, either, being the person who goes in and have all those things hooked up on you, or being the person, who has to hold the hands. This particular one, as you see over here, the belt-like thing was really a lot of sensors that can put into the belly of the pregnant woman. And the intent is for this to be non-invasively checking the fetus's heartbeat. Now you also notice there's a little clicker on the side. So most of the time that's in the third trimester, they ask you to click it so that you can kind of tell when the baby is moving. So this kind of like a little marker when you finally read the EEG graph. In this case, you will be able to kind of tell a little bit more details to it. Now, this is actually not really the system I want to talk about, because at this point, we know the baby is still safe. We're kind of just there trying to make sure there's data gathering making sense, right? The more urgent ones, more crazier ones, the ones that used to give me a little bit, really getting it onto my nerve is actually the one that they usually use when it comes to the time around the delivery time. I don't have a picture for it because it gets a little bit gruesome after a while, right? So the particular problem, as the previous picture probably can show already, is really trying to using this method, using this kind of medical devices, instruments, in order to be able to detect the heartbeat and have a clear and accurate reading in this case. Now, interestingly, this diagram is actually coming from Professor Woodrow, who obviously have a very strong marks on a lot of our signal processing algorithms. And it turns out in 1988, he actually wrote an article specifically about the neural nets and adaptive filtering. And he used this particular fetal heartbeat reading as an example. So he has a short analysis, right? So when you have this belt-like thing on the belly, you do read two clear heartbeats. One is the mother's and the other one is the baby's. And they're obviously independent. These are luckily and gratefully two independent heartbeats. But it's very difficult to actually split them apart, mainly because if you have to look at the frequency domain, that's kind of the confusing part. Now, That's why he claimed at that point in that articles, of course, like you can't really just do straightforward ordinary filtering is how he called it. And he was talking about this a great case for adaptive filtering. But in his original system, there is also another belt actually around the mother's heart so that you actually can have a reference reading out of that. So again, this is kind of how the problem, when I was lying there, had my epidural and I was having all of this hookup on me. And as any nerds would do, I think about how did they do it, right? Anyway, that's many years ago. So a little bit fast forward to more recently, methodology like deep learning, the type of processing capabilities that we now have both for our computers as well as for embedded chips, for example, are fast growing. So that really leads us to kind of take another look at this problem just to see whether there's any new interesting ways to do it. And for any of the neural networks, we need data. And me as an engineer, obviously, do not have full access to medical data. Mine probably was, discarded a long time ago. So PhysioNet is a good place to kind of hunt down some of this type of data. One of them is actually using simulation to describe both the mother's heart beating signals and the babies, and then having them mixed together to kind of construct a similar situation as you would if you had a belt like the one I showed in early pictures. So I have provided references over there. This is where I could potentially show an example how we do it. Actually, MathWorks do have an example in there that uses exactly the same data set. But, I know many of you in the audience probably have come across problems like this very similarly. And you probably adopt an AI pipeline that, be it in Python, be it in MATLAB, be it in, PyTorch, for example. So this is, really just projection to say that, yes, I know maybe this require different kind of skill sets, but this is the type of problem usually you got to solve, right? You want to make sure the data is good. We just showed how you can pull out the data, pre-process the data, and then you focus on building up an AI model and make sure this AI model can be, verified and runs fast enough and trained fast enough. And then you think about how to deploy this into a system. Now, even with this diagram, it looks very MathWorky or very MATLAB-y. You notice that, and we have to agree, and we probably can easily agree, is going through this process is not only hard, takes a lot of skills, it also, brings in this extra difficulty is not everything going to work easily, right? You have a lot of small problems to solve, large problems to solve. That's what I call the speed bumps. So that's why I'm really not here to say, our tools are the best. I'm really here to say that, like, we wanted to build a kind of a low code approach to solve all of these problems. And then it's really your domain expert that has to shine in order to solve this problem. And we have certain tools that can zoom in and focus on certain areas of this type of problem-solving progress. And specifically, as my title has indicated, I wanted to show you some of our compression capabilities. Like when you have a model trained, it might be too big to go on to an edge deployment or going on even to a microprocessor, for example. What are the tricks you can try? And what are the kind of the mathematical intuition behind it, and how we can use a low code approach to do it. So that's why I have to assume and really zoom through that this is one of those networks that actually can solve the problems we're showing. This is clear a diagram, not necessarily an actual network. To parse this diagram, the middle part is where the input mixture signal comes in. And the left and the right are both of them actually is one of those typical unit because we will pre-process the data to use the spectrogram. So that's why we're really using the UNet. Probably is, if you recall from your machine learning or deep learning 101, that's how you use this to process medical images to find the tumor. Because the advantage of UNet is that it kind of like zooms in and then zooms out and then zooms in again, and then try to match at the similar scale the type of information that you can take advantage of. So that's why the left and right is almost symmetric if you ignore the middle part of the purple arrows. So that's why if you use the right one to generate essentially your maternal ECG, and your left-hand side, I'm looking at my screen too, so my left and right may be reversed with you guys. FECG, your babies. Now, the purple one that points from one side to another with a big giant like a negative subtraction, this is really trying to address the problems where in the same mixtured ECG, if you are able to at the same scale find out your maternal potential, maternal heart signals or frequencies spectrum characteristics, then subtracting that from there, then you have a chance to much more easily identify the relatively fainted or relatively more random baby's heart design. Now, this I was able to talk against it, but of course I'm not the one who come up with it. I had also the references at the bottom where it talk about how this particular network would being able to perform the tasks as we show. So this is where we're gonna kind of start with, and also if we have this network can be trained in MATLAB, and after that you can also verify the top window in this case is the mixture signal, and then the left two, top and bottom, are the target signals. Remember, our original data was actually generated from the simulation models. So that's why we actually could get our baseline, if you want to think about, or our labeled data. And the right-hand side, bottom two, the two small ones are about the predicted signals. So visually, you can tell they're quite similar, and especially if you're mostly interested in looking for the bit, the number of bits and per minute type of characteristics, of course, they will be very easy for you to clearly identify those. And this is where our kind of trained network with no compression, mostly just about solving the original problem will land to. I'm going to switch a little bit to talk about the other problems, right? Is now how do we get them to that embedded target? Because they might just be going to be too big. So in our kind of methodology, we suggest to looking at this from two kind of consecutive angles because they're relatively orthogonal. So that's why you don't have to perform one after another. But they do falls into two separate categories. One is about structure compression. That means actually change the structure of a model, change the number of filters, reduce the dimension in order for you to get a smaller model. The second category is using play the data type tricks. Many of you have done acoustics, and you know compression in general does mean if you can represent this with 16-bit or even 8-bit, that's usually a free meal or a good deal for you to trade that off. So these are the two categories that are gonna really just go with a 100 feet type of view over it. And we're really hopefully at that, after we exercise some of this compression methodology, by generating code automatically from most of our tool chains, we'll be able to see a much smaller model that's suitable for deployability. Okay, so the term we used for structured compression, one of them is really pruning. And this particular pruning is pretty popular in the neural network type of design community, because when you train the network, but your final inference data may not be that demanding. In this case, would you be able to remove maybe some of the elements in your weights, in your learnables? Maybe you'll be able to chunk away part of your channels. or filters, how some other tools would call it, or you can completely remove one of the layers. And deciding how to do that is through an iterative pruning process that kind of learns and tries whether this meets into, if I get rid of this, would I still be able to produce very good results? And in our product groups, we do use Taylor scores in order to keep track of that. We also have followed methodology like SymFlow, which is also a way to be able to identify which are the layers filters potentially is good to be removed. Okay. The other category is we call it projection. And projection itself is actually very much what MathWorks do well at. We do principal component analysis right after the projection to a subspace. So this comes from the fact that you actually are carrying through all these vectors around. And then if you think about particular layer implementation, is indeed step one, being able to project it to a subspace, which is one way of reduce your dimension. And after that, if you were able to use your eigenvalues to search for your most important components, and that is the only thing you want to keep. So this is really another pruning technique that changes structure, specifically the dimension of your original design, without hurting, again, the performance of your neural network. So these are two tools that kind of you can quickly actually find it out once you have your pre-trained network, which I will have a short life demos about. And then this tool, this kind of dashboard was able to show you what kind of layers you have, what kind of parameters you have, or learnable specifically. And for each different kind of layers, in this particular example, there are many conv1D layers. So they may be able to be pruned. Now, we call it a maximum compression. That's because this is really basic analysis, but this is not yet being able to run and iteratively refine with your network. So the actual workflow, sorry, my screenshot actually cut it out, is there's next steps to show how you can build up script in order to be able to prune along these lines utilizing this methodology. I'm done with the two ways of doing compressions of structure compression. I'm going to quickly jumping into the quantization aspect of it. So quantization is really going with, the basic discoveries about that maybe we don't need single precision. It's too much, too big, don't have space for it. So what kind of lower precision data types or really integer data types we could choose. So the guidance of this app is really just walk you from left to right and following along about choosing a network, finding out the right data set for you to drive your model, to identify what kind of ranges, both your, not only just your weights and biases, but also what your activation output gonna be, and then being able to quantize and validate whether that's supported. So with that, I'm gonna lead into one recorded live demo. There is no sound to it. This is just a recap about what we kind of wanted to show. This is the demo, this is the examples that I was referring to. And this is that the data can be loaded. This is the type of input data we could get. This is the network used in here, bunch of MATLAB code. And here's what the predicted output. And this is very similar to what I showed by running through one of the channels. Now, we want to know what this final networks look like. You probably guess it's like a 195 layers, and it will be able to run the analyze network by directly feeding this network into the UI. And this brings up a detailed view, as you see on the left-hand side. That's that WNet. That's why I use that diagram, because now it's really hard to see them. And you can also find the different dimensions for the network. Then when you run the analyzer, you're already set on that particular network, right? So here I'm going to use the designer, which is really give you an iterative way of improve your design. In some cases means adding new blocks, adding new layers, changing your input. As you can see in the overview, this has a WNet structure, it's just that doesn't curve back. I'm showing one of this compression technique, compression dashboard I just showed you, and as it brought up, you will be able to see the similar life analysis as I just showed. It has the table at the bottom. In this in this video, I left it a little bit too small, so that's why I ended up scrolling up and down, harder to read than my screenshot. Yep. So this really gives you some kind of quick estimation or even guesstimation about where you probably want to start to slay your dragons or squeeze it out. Okay. Yeah, so in this particular demo, I didn't go in and actually exercise that read about next step. So I didn't run any script to actually prune the model at this point. I went on and opened up the deep learning deep network quantizer, which is the second GUI I showed, or the third now. And here we're going to be loading in that WNet variables as we just look at it together. And as you can tell, it has different kind of execution environment because we want to be able to match the quantization capabilities or running integer layer capabilities through different target. We'll load that ECG data, which is the mixture in the form of a DL array, which is a data formatting for arrays that can use for DL network. And as you can see, the activation output of different kind of layers are included. You can click on the quantize button. Actually, in this particular example at this point, there's really not much to see because we know it's unlikely to work with 8 bits. So in this case, it doesn't recommend to truncate it into 8-bit because that's going to miss a lot of information. If we do, then we'll be able to validate. So here I'm showing a kind of some of what I would consider again as a low-code workflow. Is you would have run this calibration for long, and you want to share this with the rest of your team, for example. You can reload this quantizer workflow object, and all the information will be brought back. So this is really more about exercising different kind of compression techniques so that you would really play on the same model and understand what kind of impact it can have. So this is the end of the recording, and hopefully I should be able to advance. Yes. So this is kind of where I wrap it up. And being able to show what we have in here is really the capability of walking through some of this AI pipelines and being able to highlight some of these compression techniques on a particular example that may or may not relevant to your real life. And with that, I'll be closing with my own contact information. You should be able to find me at LinkedIn or, you know, Francis has my phone number too, so we'll be able to reach out to me. Thank you.
Do we have any questions? Okay, well, thank you, Brenda. And Matt, how are you, Matt?
I'm good. How are you?
All right.
All right. I'll share my screen. Can you see my screen?
Yes. Thank you.
Cool. Okay, so hi, my name is Matt Daly. I'm a technical writer at MathWorks. I'm also a part-time master's student at Johns Hopkins, and I'm presenting on a submission I made to one of the ICAST 2024 grand challenges, which was the Cadenza challenge. So I worked on this. The challenge ran from September to December of last year, and then I just presented this at the ICAST in Korea a few weeks ago, but I'll go into more detail on this. So a quick overview of the Cadenza project. It's a UK government-funded research project that focuses on improving music signal processing for people with hearing loss. And they organize machine learning challenges like the one I'm talking about that I participated in. to kind of advance the research on music signal processing. And another thing is closely related to the Clarity project, which is similar but focuses on speech processing instead of music, but also for hearing aid users. So a quick overview of this specific challenge. The goal is to design a system for remixing music for hearing aid users. So the inputs were music that a user would be listening to, and desired gains for different tracks, which were the vocals, drums, bass, and an other track. So the goal would be to remix the levels of these different tracks for the desired gains that a listener would prefer. And another input was the listener's characteristic hearing loss, which was in the form of an audiogram. So in this diagram, the music enhancement block in the middle would be where the user's system would go, and its output would be evaluated with the hearing aid audio quality index, or HAQI metric, which is an objective audio quality metric that takes in a signal and a ground truth reference signal and outputs a value between 0 and 1, measuring the quality of the signal relative to the reference, and that this metric incorporates the audiogram and the hearing loss characteristics. So to evaluate the systems for the whole challenge, the systems were evaluated on a test set and then averaged together all the HAQI scores for all the different examples. Yeah, so this is an example of the audiogram that I was talking about, measuring the hearing loss of a specific person, and it would have both the right and left ears, and then at different frequency tones, we can see different levels of hearing loss. So the data was a data set of music tracks, and then it had the ground truth separated tracks with the vocals, drums, bass, and other from this MustDB 18HQ data set. And another aspect of this specific challenge was that the music signals were convolved with head-related transfer functions, or HRTFs, to simulate different head positions when listening to the stereo speakers, like in a setup we can see here. And we can see how this would incorporate kind of crosstalk between the different channels, where the parts of the signal from the left stereo speaker would go to the right ear listening channel, and vice versa. So this was another aspect of the challenge specific data. So this is a block diagram of the baseline system that was provided by the challenge that my system closely followed in terms of its architecture and structure. And we can see on the left, this process music block splits the input mixture signal into the 4 different estimated tracks. So in the baseline, this just used like the off-the-shelf pre-trained HDMUX music source separation model. And then once we have the estimated separate tracks, given the desired gains from the listener, it would just perform a simple weighted sum of all those tracks now with the desired levels. For example, a user might want the vocals to be boosted by 10 dB or something like that. And then after that, there's loudness normalization, and then this NALR amplification, which amplifies different frequencies in the signal based on that audiogram. So based on the hearing loss characteristics, it will boost different frequencies to compensate for the hearing loss. So like I said, my system followed this overall structure, but I decided to focus mainly on the music source separation aspect to try to improve that and improve the quality of the overall system. So to do that, I fine-tuned existing music source separation neural networks. So these are the different architectures that I used, and I took pre-trained checkpoints and fine-tuned them on the challenge data, which incorporated those HRTFs. So these are the three architectures: HDMUX, QuiLab, MDXNet, and DTTNet. In general, all of these use an encoder-decoder unit architecture for the music source separation. And I fine-tuned them on the challenge data, and I actually found the best results in the end by using an ensemble of all these fine-tuned models and just averaging together the predicted signals from the outputs of these networks, and then using those separated tracks to do the remixing and output the signal of my system in the end. So that was the main thrust of my work, but a couple of other things was at inference time, I incorporated the residual signal to predict the other track. So this diagram is my attempt to explain this. Theoretically, if the vocals, drums, and bass signal that were predicted from the music source separation were perfect, then just subtracting all of those from the original mixture would give the perfect other signal. That isn't the case usually, because those predicted vocals, drums, and bass tracks are not perfect. So pretty much all the music source separation networks directly predict an other signal. But we can actually still incorporate this residual signal in the final prediction at inference time. And that's what I did by just taking that and averaging it together with the predicted output from the network and using that as the predicted other track. So that was an aspect of my final system in the music source separation component that led to good results overall. And then another aspect was clipping. So for cases of severe hearing loss, with audiograms that had that severe hearing loss, that NALR amplification would boost the frequencies that had that severe hearing loss. Would boost those frequencies a lot in the output signal, and that would cause clipping and distortion, and that hacky metric was affected by that clipping if there was severe hearing loss. So in my system, I just used a rough heuristic to detect when the clipping was bad enough, and then when that was the case, apply an audio compressor to try to mitigate that, and that also seemed to help. So now these are the results of the hacky scores averaged over the final test or evaluation set for the Cadenza ICASP challenge. So this is the baseline at around 0.56, 0.57. And these are the separate fine-tuned networks I have listed ranging around like 0.6, 0.61, but then actually including the ensemble improved it a lot, and I got to 0.63 for the final Hacky score, and this was actually the top score in the whole challenge. And then I also performed a couple of ablation experiments. So in this first one, I wasn't using that residual incorporation that I mentioned, and the performance went down. And this other one, I wasn't using the audio compressor to try to mitigate clipping. So the performance went down there too. So we can kind of see how those aspects, as well as the ensemble of the different models, were kind of important to the final success of the system. Now, yeah, just a final kind of note on how MATLAB could fit into this. I implemented my system in Python using mainly PyTorch, because that's what the challenge called for. But since I work at MathWorks, I decided to try to create a little demo that would show how to process one of these examples using like the baseline system to perform this remixing and enhancement. I was able to do that still using Python co-execution for the neural networks to call the inference for that on the music source separation. But just a couple of highlights of what I thought MATLAB offered in that respect was the relatively new like SOFA functionality in MATLAB for reading and analyzing SOFA files, since we had these HRTFs that were originally stored in SOFA files. We could use some of the visualization functionality to analyze those. On the right here, we have a screenshot of the frequency responses of the different HRTFs. And then another aspect is that Hacky metric actually was pretty slow in its Python implementation. That was a bottleneck during development for the system. But in MATLAB, it was relatively easy, very easy actually, to just parallelize it because it performs a gamma tone filter bank filtering, and just kind of changing some for loops into par for loops significantly improved performance. So yeah, roughly evaluating a 10-second signal went from 7 seconds to 3 seconds. And in terms of like evaluating a system on the whole test set, that would have been significant while developing. But yeah, I'll stop for questions now, but you could also email me if you have any other questions. And there's also the paper, the technical report that was part of ICASP, and that's on archive, but that should be on IEEE Explore, I think, in a few weeks. But yeah, let me know if you have any questions. Thanks.
Sorry, in the back.
So now R is a really old fitting formula and just does fixed gain. You're looking at the audiograms, the parameter of this thing, which representation of our lowest hearing threshold, but we have an upper hearing threshold as well, which doesn't really change much with hearing loss as compared to a normal hearing person. So what you really need to do is compress the dynamic range of your signal into the range in which that person can hear it. And I think you would do a lot better if you did that as opposed to just boosting and boosting stuff out of the natural dynamic range of the signal. So I'll probably choose something more modern.
Yeah, so that was actually part of the challenge itself, was that Nalar amplification. I think it has to do with hacky, the metric itself. In the reference signal, it is applying the Nalar amplification. So for whatever reason, that was part of the specification of the challenge. So I didn't really mess with that part, and trying to improve that and just focus on the music source separation.
Okay, sorry, the push, yes.
Hi. Well, thanks for the talk. I don't know much about perceptual audios. Maybe this is a silly question. But what happens if you do nothing? What is the hacky score if you do nothing?
So what do you mean if I do nothing? Like at
how would the person perceive the mixture of all these components if you did nothing to separate them out? I mean, you're trying to make them hear better and improve the hacky score. So I'm just wondering, how much did you improve over the worst case scenario? Is there such a thing over there, or am I completely missing?
Asking for baselines.
I'm just saying, if you don't do anything, what happens? How does the listener hear?
There was a before, but it included a model, right? Like it was like in the chart, it was like the
yeah, I thought there was a baseline model.
So it is processed, but there is no like quoted unprocessed score, right?
Yeah, so I think I mean the reference signal for the hacky score, I guess, in this diagram, like that includes the ground truth where the perfect separated signals are remixed to the desired gains. So if you were to not try to remix the signals to match that, since it's an intrusive metric, so you're trying to essentially just match that ground truth. If you were to not separate and remix, you would do pretty bad, I would think.
Yeah, I'm just wondering how bad, so that your 0.63, that you could compare it to that really bad situation. That's all.
Right. Yeah. That's a good question. I didn't do any baseline testing with that more naive approach, I guess.
All right. Thank you.
Sorry.
Thanks.
Yeah, for the technique of averaging the residual source signal, so it works. But I wonder if there was a like theoretical reasoning or motivation behind it.
Yeah. So that's a good question. Probably more investigation for like reasoning behind it would be beneficial. But in general, for these music source separation networks, the other prediction is usually performing the worst, because if you think about it, it has less characteristic aspects to it. It could be across a variety of genres. The other part could be a lot of different things. So I think in general, it's not, those predictions aren't great in the first place. So they might be missing a lot of components that could just benefit from that simple residual incorporation. But beyond that, probably more investigation is warranted.
Have you ever tested just using the residual, not using the other predicted others?
Yeah. Using just the residual is at least in like my smaller test that I was working with, that did not do well at all. Like it was much worse than just like directly predicting the other signal. So on its own, it didn't seem to do well, but it did have some information that was useful combined with the other prediction.
Okay, thank you. That's interesting.
Yeah.
Oh, sorry.
I have a question about why are these the 4 categories? So I've seen them before in literature, but I just don't know why. Why can't I have like a violin and a clarinet? Or are there any open source models that will do each instrument? And if anyone else knows, I would like to know.
Yeah. So I'm definitely not an expert in this, but I think it's mainly just like a limitation essentially based on the general genre of music that is used in the the training data, and having specific tracks that for the ground truth that you're separating out. I think there are data sets that have more like annotated separated tracks, and that you can probably apply similar models to separate out those instruments as well. For this challenge, I think the challenge organizers just kind of took the basic standard that seemed prevalent.
Okay, thank you.
Okay, well, thank you very much. I think we would take 5 minutes break so that we can set up the PC for the next speaker. Thank you very much, Matt.
Thank you.
Thank you.